Hey, it's me, Destin. Welcome to Smarter Every Day, and today we're going to show you some pretty cool high speed, and it has nothing to do with all those assault rifles. It's actually much sweeter than that. Literally. Check this out. It is a jar of honey. So, I know this sounds a little strange, but we've got a high-speed camera set up, and we are going to show you something called the liquid rope coil effect. This is how it works. You just put some of the honey on this chopstick here and you just drip it down, and look at this. Check out that. How cool is that? It has to do with the viscosity of the fluid, and basically the liquid is piling up. So I think this is really, really neat. So we're going to get a little bit of high speed of it, and then after that we're going to discuss this in more detail. Fluid dynamics are awesome. It's tempting to think that this would be an easy math problem, but it turns out people have been studying this for 50 years. To explain, let me show you the variables. This section is called the coil, and this section is called the tail. The coil and the tail together make up the total height h. The mass flow rate of the material is q, and the initial radius at the top of the tail is called a sub 0. We'll call the radius at the bottom a sub 1, and the exciting part is the angular coiling frequency, which is omega. The fluid itself also has internal properties that we have to consider. Density is rho, and the surface tension coefficient is gamma. The kinematic viscosity is nu. Okay, simply put, viscosity is the measure of the thickness of a fluid. Viscosity is the measure of a fluid to resist a shear or tensile stress. Dynamic viscosity is measured in poise, whereas kinematic viscosity is measured in Stokes. Kinematic viscosity is also referred to as the diffusivity of momentum, and that makes sense if you think about it, to diffuse momentum throughout a fluid. As you can see here, obviously the molasses honey mixture is the most viscous. Okay, if these big words are boring you, just wait, there's a shower scene for you. But if you're like me and you want to understand what's going on and you want to know the math, let's do this. What you're looking at here are the 4 different types of flow that scientists can describe using the variables that we defined earlier. Let's start here with this one. This is the viscous flow regime. The way it works is as h, or the height that the fluid is dropped from, is relatively small, the flow has to naturally go into a spiral because the fluid has to get out of the way of itself. Now, the interesting thing about the equation used to define the coiling frequency is that it doesn't even include the kinematic viscosity of the fluid. That's interesting, seeing how it's called the viscous flow regime. Okay, the second condition we're talking about here is called the gravitational flow regime. Basically the way it works is as that height increases, gravity begins to take over and stretch the fluid. So basically the viscosity of the fluid is resisting that stretching, and that's why the equation there shows that kinematic viscosity starts to come into play. That's where the coiling becomes uniform and stable. That's the exact condition that we were filming with the high-speed camera earlier. The third condition we're going to talk about is called the inertial regime. Now, as height gets very, very long, what happens is that fluid becomes very fast and very, very skinny. Now, you'll notice in the equation that the radius of the coil at the bottom is factored into the denominator and raised to the 10th power. Now, if you think about it, that means the smaller the radius gets, the higher the coiling frequency, which makes sense. Okay, the fourth regime is why I love science. All we know is that somewhere between the gravitational regime and the inertial regime, everything goes out the window. All of a sudden you'll go from a steady state coil to some erratic figure 8 pattern or something stranger. But if you raise it just a little bit more, all of a sudden you're steady state again. Even more and you're back unstable. Everything is erratic. The frequency is varying wildly, but it seems to have some sort of pattern, but we don't know why. It's very interesting, and there's been a very complex study done on it, and I'll leave a link in the description to that so you can check it out yourself. I think it's amazing that we as humans can conquer so many things about the world around us, but we still struggle with the smallest of things. If you're interested in knowing why I did this video, I'll leave that info in the description as well. Boy, that got weird in a hurry, didn't it? Every single day you can check out the liquid rope coil effect in your own shower. It's pretty easy. Just take your shampoo, which is a pretty viscous fluid, and throttle the flow rate and the height until you get the right combination, and then boom, you lock in on the liquid rope coil effect. It's pretty cool. You can change things and see how the variables affect its action. Anyway, I'm not responsible for any extra shampoo you end up using. I'm Destin. You're getting smarter every day. Have a good one.